All right, let's get started. Get the lights and whatnot adjusted. So, I'm going to remember that. I'll pause the recording. I'll tell you all the answers to the final. How's that?
That sounds good. Sounds great.
You missed it. I told everybody the answers to the final. And I paused it on the recording, so it's not on the recording. Oh, I'm gonna have to ramp that exam up then a little bit. All right. A couple announcements. I extended the deadline to Homework 6 to April 3rd. This is our last time that we meet before you turn it in. So does anybody have any questions? Hopefully you've started it. Yeah. Now, Now you all know that you can do problem 1 and 2 right now, and to be honest, you could probably muscle your way through problem 3, but definitely after today, you'll be able to do problem 3. I'm assigning concrete homework on Monday, so, and I pushed our exam back in there 1 week, so it'll be on the 12th. So, that's okay? Yeah, it was supposed to be on the 5th. Yeah, but I will explain that when we get closer to it. Okay, so there's really no other announcements other than I hope you all brought a straight edge. Now, honestly, for the purposes of today, if you can get a straight edge, you're probably good. So anything that you can use to use a straight edge, if you want to use the edge of your notebook or something, that might actually be fine. But the big thing is, hopefully you all have your alignment chart. I plan to, or hopefully try and at least use this today. If not, we will definitely use it Monday, Wednesday, and probably Friday. So you definitely need to be bringing the straight edge for the next few lectures. Okay. With that, I'm going to shut up and get into the wonderful world of columns. So last time, this is where we left off. We started the world of column design. Instead of giving you a column and determining how much load will cause that column to fail, we then flipped it and we said, all right, let's handle a problem like this where you have no idea what the column looks like. If I give you the loads, what column must be selected or should be selected in order to safely resist those loads. So there's our tenets of column design. Now the first problem that we did was this one. The purpose of this problem was really to just try and get you more acclimated with how to select trial shapes in the design aid in table 4.1. What made this problem easy was that the boundary conditions and the column lengths were the same in both directions. And if your K is the same in both directions and your L is the same in both directions, then the weak axis automatically governs and you don't need to go back and check the strong axis. However, on this one, not the case, because we have different boundary, well, we have this, we're going to ultimately have the same K value, but we have different lengths in different directions, so we're going to have to do a little bit more work on our designs. So in the last problem, when we picked a member, we knew it worked because the strong axis and the weak axis was the same in terms of boundary condition and length. It isn't the case here, so when we pick sections out of table 4.1, they are going to be trial sections. We're going to have to do some work to assess those sections. All right. So let's just make sure everybody's clear on the problem. So we're going to be designing a column to withstand a load of 890 kips. So one point I want to mention right now, we're going to do some math with table 4.1 to select a shape. Anytime you arrive at a final column section, your next step should be to check that capacity using either the equations or using table 4-22. I mean, again, we're talking about a column that we're designing to hold up 890,000 pounds. Okay, so I think it behooves you to do a little bit of math. All right, I don't like columns falling down in buildings that I'm in. So I think, I get it. It's homework, and you don't want to do it. It's worth it. Okay, so we're selecting a column to withstand 890 kips. We have Fy as 50 KSI, which means we can use table 4.1. Now we have a 20-foot long column, but it has different boundary conditions. On the strong axis, we have a length of 20 feet, but on the weak axis, we have it braced intermediately. So, everybody okay with that? Now, let me ask you this. What is the K value going to be, well, I guess for the whole problem, regardless of what direction you look at, what is K going to be? 1, right? Because regardless if you're looking at the strong axis or you're looking at the weak axis, every segment, every unbraced segment of this column is experiencing pin-pin boundary conditions. So that's where the K equals 1 comes into play. Okay, that's my first question. My second question is, if that's the case and K is 1 everywhere, if we're looking at the weak axis, which segment do we really need to be worried about on the weak axis? We have 3 unbraced segments. Which one do we really need to concern ourselves with? The middle one, because it's the longest, right? Longest segment, longer lengths equals larger slenderness. Larger slenderness equals weaker column. So the longest segment is the worst case scenario. So we're going to focus all of our efforts on column selection on that center shape, or that center segment. Everybody okay with that? All right. So, what's up? Oh, there. Where'd my pen go? Oh, here's my pen. Okay, so all right, so the first thing that we would typically do on a column design problem is determine the factored load. But we really don't need to do that for this because it was given. So PU is 890 kips. Okay? Now, for the column, there's a few things that we can write off the bat. So first off, we know that our yield stress is 50 KSI. And we know the following, okay? What is KL in the x direction going to be? Can y'all do some work? 20. Or if we want to be diligent, we can say, okay, 1 times 20, just to indicate that we're recognizing that K is 1. So if that's for the x direction, for the y direction, it's 1 times what? 8. Remember, that's the center segment. Sound good? Okay. Now, on our previous problem, KLX and KLY were equal, so we really didn't need to go and check KLX. Oh, what did I do there? What was that? Goodness. That laugh, I'm getting ahead of myself. That laugh was well deserved. I'm doing it again. My coffee hasn't kicked in. That laugh was well deserved, so I totally earned that one. All right, we're at 6. I'll go ahead and say it. We're at 6. Since I wrote a 6, we'll say I'm on mistake number 7. No, it's just how many I'm allowed. I haven't gotten to 7 yet, so we'll see what happens. We've never hit a 7 before. All right, going back to this, so if KLX and KLY are equal, we really don't need to worry about the x direction, because if we look at KL over R, since RY is always smaller than RX, we know that the weak axis is going to govern. But since this value is larger, since KLX is larger, what we're going to have to do is we're going to have to select columns based on the weak axis, but then for each one of those columns, go through and check the strong axis. So let's take that one step at a time. So the first thing that I want to do is I want to get some trial shapes, so some trial sections. Okay. Now, these trial sections, we're going to get these out of Table 4.1. Now, remember, Table 4-1 is built based off of the weak axis, okay? So what I've got to do is I've got to look up sections with the following. We have to look up sections that have a PU, or a PPN, I guess I should say, of 890 or higher, and a KL in the y direction of 8 feet. So you remember how this works, right? We start off with the W14s, and we ask ourselves, what is the lightest W14 that's available that will adequately withstand 890 kips at a length, effective length of 8 feet? Okay, the 82. You're saying the W14 by 82. Does anybody second that choice? Okay, all right. So you're saying the W14 by 82. Now, just so everybody's clear, you picked that because it has a PPN of what? 960? 968. Okay. Now the next lightest section is a W14 by 70, was it 74? That one, what's its capacity at 8 feet? 879, so it's not good enough, okay? Now, let's be clear, all right? Let's say I stopped right now, just stopped. Would I know right now that the W14 by 82 works? No, because I'm selecting it based solely on the weak axis. I would have to go and check the strong axis. All right, let me do something real quick. All right, now, if you recall, when we did our analysis example with this table, there was a ratio that we needed to do a little bit of work with. There was a ratio. Do you remember what that ratio was? Maybe Rx over Ry. Remember that? Yes, exactly right. Exactly right. If KLX is larger than KLY, we need to do this additional check. If they're equal, we don't. And if it's less than, well, that would indicate a design that really doesn't make a lot of sense. I mean, the strong axis isn't what really needs the bracing in those instances, the weak axis. Okay, you had a question. We're not done. That's this one. So since you brought it up, all right, hold on. First off, what's the Rx over Ry for this shape? Because we're going to need it. Say it again. 2.44. Okay. Now, Mr. Lewis, what is the lightest W12 that would work? By 190. What length are you going off of? What'd you say? 79. Do I have a second on that? Okay. Now, do you see why we're picking that? Well, first, what's your capacity for that? Say it again. 971. Okay. Do you see that? Okay. You were looking at 20. Well, that's why. Okay. Again, on the left side of that table, it says effective length with respect to the least radius of gyration. In this case, Ry. Now, in order to check this, we're going to need Rx over Ry. So what is that? Say it again. 1 point. All right. Now 3. A W10. Say it again. 77. Do I have a second on that? Now, believing him. All right, what's the VPN for that? And it's Rx 0.73. Okay. Okay. Now, what I'm going to do is I'm going to take these shapes one at a time, and I'm going to analyze them about the strong axis to see if these sections are valid, okay? So we're also going to use a little bit of common sense when we do this work because I'm lazy, okay? And I like to reduce the amount of math if at all possible, okay? So you'll see where that goes. So let's take these one at a time, okay? So let's start off with trial section number 1, that W14 by 82, okay? Now we know that that section has enough capacity about the weak axis. We do not know if that section has enough capacity about the strong axis. In order to quickly verify that, we need to convert this into one of those effective KLs. So in order to do that, we take KXLX divided by RX over RY. Okay? So that's going to be 20 feet divided by RX over RY, which for the W14 by 82 is 2.44. Okay? So what does that come out to be? 8.20. Okay? Okay. Now, what we can do just conceptually is we can compare this to KLY. So this KL effective is 8.2 feet, KLY is 8 feet. So by looking at this and KLY, we can compare apples to apples. And what this tells us is that for this column, since this value is larger than 8 feet, it tells us that the strong axis, in fact, actually governs this column. Okay? Remember when we did that analysis example, we had KL over R for all those different segments, and the largest KL over R governed, and on that example it was actually the strong axis? That'll happen on this one too, okay? So is everybody kind of okay with that? Does that make sense? Okay, all right, yeah. So we have KL effective is 8.2 feet, right? And we have KL Y is 8 feet. See, we can't compare this and this because it's like comparing apples and oranges, okay? But by making this conversion, we can now compare these apples to apples, okay? And since this value is larger, it tells us that the strong axis governs. Does that make sense? Here, if that's a little hazy, let's look at this, okay? So let's say we've computed this value, right? So if I want to determine the capacity, that means I need to interpolate. Make sense? So I need to interpolate between, what, a KL of 8 and a KL of 9? Sound good? So what do we have? We have PN at KL of 8 and a PN at a KL of 9. What do those come out to be? You've got the table, right? Now you should know the top one. We looked that one up. The 968, yeah. Okay, what's KL of 9? 940. So far, so good? Okay. So what I'm getting at is that the capacity is somewhere between these two, right? Which is smaller than what it was for the weak axis, which was just the 968. Does that make sense? Now, here's the real question. You agree that the capacity is somewhere between those two values, right? Do I need to do the math? Why? Thinking man right there. Doesn't matter what that value is. It's somewhere between 968 and 940. Whatever it is, it's higher than the load, right? So what I am proposing is that the W14 by 82 is good. Okay? So I'll put down here no interpolation necessary. Okay, does everybody understand, and this is really important, does everybody understand that no interpolation is necessary? Does everybody understand that? Okay. Now, if we stopped right now, just stop the problem, and said the W14 by 82, it will work. It is a safe column to resist those loads. Should we keep moving on? Should we press forward? Because we've got other columns that are lighter, right? We have the W12 by 79. We have the W10 by 77. So let's keep going. A common question that students ask is, well, why don't you just start at the lightest column, and as soon as you find one that works, stop. That's totally fine, okay? No, that's fine. In fact, I would encourage that. The reason why I'm doing it this way is just because I want you all to have more and more practice doing it. So, see, I want you to be comfortable with it. Critics. Has everybody got this? Okay. So let's do it again. Let's do it for shape 2. So shape 2 is a W12 by 79, right? So what we're going to compute is its KL effective, which is KX LX over RX over RY, which is 20 feet divided by, what was the ratio? And what does that come out to be? 11.43. All right. Everybody okay with that? So 11.43 feet. Now, obviously the table doesn't have a value for 11.43, but it has one for 11 and 12, right? All right. What's that? Well, what are the values? 910 and 887. Now, what are you saying? It's not going to work. Okay. How will we know? We got to do the math. Unfortunately, this one is between the 910 and the 887. So the load. So yeah. Now, I'll be honest. Looking at these numbers, it probably is going to work, but we're. Wonder how that works, right? Remember, you're taking your dead loads and upping them 20%. Your live loads upping them 60%. Your column capacity lowering it 10%. So all right. So let's see. Let's do a little bit of linear interpolation. So what we got? We got 910 plus, and we take our difference, 11.43 feet minus 11 feet. You all are experts at this, right? So 12 feet minus 11 feet. What's that? See, this is, so linear interpolation, that's a formula sheet one, right? All the way back to engineering 111, right? Y'all should be experts at that. Oh, yes, you can. I believe in you. That's all it is. That's exactly what it is. So, does that one pass the Cruikshank's test? Why not? It's A992 steel is what it is. It meets the ASTM spec. All right, no. We're stopping that right now. Is this column good? Yes or no? Yes. All right, thank you. Okay, and the reason why this is good is because PPN is greater than PU. Okay, so one of the things I guess I ought to mention right off the bat is the measure of efficiency that we did before. Sometimes it really doesn't work when you're dealing with columns and beams. Remember how we took the load and divided it by the resistance to get the measure of efficiency? Because the equations are very, very nonlinear, sometimes you can have a column that has a low efficiency, but it's still the most economical selection. And how do you know it's the most economical selection? Because we're literally cycling through every single column in the manual. So, you know, the measure of efficiency really isn't a big deal. All right. Should we press on? Should we press on? But why do you say might as well? What's the next section? A W10 by 77. So it's lighter, right? So this is a W10 by 77. It's lighter than the one above, okay? In other words, if this was a W10 by 87 and this is all we had, I'd stop, right? There's no point. It doesn't matter if it works or not. We have a W12 by 79 that's just fine. But if this is lighter and still resists the load, do the math and check it. So let's see what we got. So we have a KL effective which is 20 feet divided by what? And what is that? All right. So that means we need a PPN and a PPN and what do we get when we look those up? Wait, what? No, that was for the other column. We got to look it up for this column. Now, what'd you have? Does everybody else see that? So should we, I'm lazy, should we do the interpolation? Why? Well, the accuracy, okay, so you're two things. Whether or not it's accurate doesn't really matter because once you pick your final shape, you're going to go back and analyze it using section E3 or the KL over R tables or what have you. So the accuracy, you can handle that by just analyzing that column just as if it's an analysis problem. But what was your second point? It's below the load. It doesn't matter what the value is. We know it's between 846 and 816. Even if it's the high, even if it's the 846, it's no good because the load is 890. Okay? So I'll put no. No interpolation necessary. What's that? Okay. See, it took a while to find a load in a KL that I had a little bit of time getting the perfect problem for this one. Oh, did you like that? Did you like that? Okay, all right. All right, so of our three shapes, one of them's no good, two of them work. Of the two that work, which one should we pick? We don't really care about the most efficient. We care about the one that's going to hit our wallet the lightest. So which one's going to hit our wallet the lightest? The W12 by 79. The efficiency measure actually doesn't really matter. Okay. So use a W12 by 79. And I'm going to put a note here on the side. You need to verify the capacity. Use E3 or table, capitalize that. Use table or use section E3 or use table 4-22. That's really important, okay? Because again, we're selecting a column to hold up 890,000 pounds. I think it behooves you to do a little bit of math to ensure that that column works, right? So remember, we've got our section. We can compute KL over R, use the KL over R to calculate F critical, and then phi PN is phi times F critical times the gross area. We have a column. It's a W12 by 79. We should validate that capacity. I mean, what did we calculate as the capacity for that W12 by 79? It was what? It was 900.1 kips, right? So if you do the math in the using section E3, as you said, we're linearly interpolating, so there's a little bit of inaccuracy, but it should be close to 900.1. It should be maybe 900.3 or 899.9 or something like that. But we know that it's done correctly. We should be good. I mean, and again, you're only going to know that if you go through and do the analysis. Okay. Everybody okay with that? So on problem 3, it states, design the column, but then go back and check it. Okay. And that's going to be a big thing that I'm looking for. Sound good? Okay. Now. Any questions? Yes. What do you mean?
I don't know, because I'm confused about it.
Okay. That's a good question. No. Okay. I see what you're saying. What I'm saying is this. It doesn't really, if you're trying to make some, or come up with some rule as to which one that governs and it's confusing you, then don't think like that. Just do this. Calculate KL over R here, KL over R here, KL over R here, KL over R here. Whichever one's the biggest, just go with that when you compute your capacity. No. Weakest. KL over R is a measure of slenderness. Okay? The larger the KL over R, the more slender the column. Okay? Now think you're taking a member and you're pushing on it. Okay? So think about it like this. Would you agree that if I'm taking a member and I'm applying compression, then something that's shaped like a soup can is going to behave differently than something that's shaped like a drinking straw? And the reason why is because the drinking straw is more slender. The larger the slenderness, the weaker the column. So if you're trying to determine, well, does the strong axis govern or the weak axis govern, and that's confusing you, well, then don't think of it like that. Would you agree that there's 3 segments of unbraced length about the strong or the weak axis and 1 about the strong axis? And you could compute a KL over R for this, a KL over R for this, a KL over R for this, and a KL over R for this. Whichever one of those 4 is the largest, just go with that to compute your capacity. And that's really, if you can handle that, then that honestly that'll remove just about all the confusion, because that's basically it. What I'm saying is that if I take this column and I apply load, there's a point at which it's going to want to buckle. Okay? It's going to buckle along the direction that has the longest slenderness or the largest slenderness. Make sense? That's basically it. Sound good? Any questions? This is good stuff. This is really, you want to make sure that you're understanding this. Okay. Now, here's the confusion. There is a difference between how what I'm calling a singular column behaves and how a column in a frame behaves. Let me just introduce the concept by saying every single thing that we have done up until now, if we ask ourselves, well, what's the difference between doing a problem with a column by itself and doing a problem about a column in a frame, the only difference is K. Okay? Everything else is the same. The column curves, using table 4.1 to pick a column, all that is all the same. The only difference is K. Okay? Now, I'm not going to lie, it's a big difference because there's some work that has to be done in order to get K, but that's the only difference. Okay? Now, what I mean by a column in a frame as opposed to a column by itself is I'm talking about the portion of the system that provides lateral stability. You remember that example I talked about way back in January when we were talking about the person in the car and the passenger not wearing, or hopefully wearing their seatbelt, and they're driving 50, 60 miles an hour, the driver hits the brake, passenger flings forward, right? Remember, the entire car does not hold you back. Instead, a particular system in that car holds you back. We call that system the seatbelt, right? The same thing is true in a building, okay? This building has dozens and dozens of columns. Not every column is part of the lateral resisting system. Only a few of them are, okay? Most of the main columns in the main body of the building are just there to support gravity load, and that's it. So all these columns in the main body of the building, you would treat them as singular columns. Just look up a K, pick a column like we just did, and move on, and that's all there is to it. The columns, for instance, that more often than not when you're talking about moment frames and brace frames, they tend to be columns, at least in this area, that hug the exterior portion of the building. If I had to wager, this column right here and this column right here are probably part of a moment frame. The idea is when wind hits the building, or if we were out in California, earthquakes hit the building, these columns are part of the system that keeps the building upright from those lateral loads. Okay? Does that make sense? There are two types of frames that we use, and two main types of frames that we use in steel design. There's a number of other options, but more often than not, you're either dealing with a brace frame or you're dealing with a moment frame. So if you look at a typical building construction, a brace frame probably looks something like this. So there's a number of different orientations of braces. You could have X braces. These are called sometimes called inverted Ks. Sometimes they're called chevron braces because of the way that they're oriented. You could have V-shaped braces. The shape really doesn't matter. The point is, when I apply a lateral load to this building, in other words, like a wind or a seismic event, these braces are keeping the building up, acting as a truss. That's basically what they are. They're a truss. Here's your supports on the ground. You apply a load, method of joints, method of sections. You all remember that stuff, right? Okay. The point to make, though, is that truss is not everywhere, okay? For instance, here's the building. We only place that truss system in a few key locations. We don't place it everywhere, okay? So my point is if I was designing the columns in this building, all the columns in the inside of the building, and this one, and this one, and this one, and this one, and these two, and these two, would all be designed as singular columns. The only ones that I would design as columns in frames would be the ones along here, because those are part of that system that's keeping the building upright. Make sense? All right. Did the chevron, did that turn people's heads a little bit? It is called a chevron brace, not like the gas station. No, go ahead. All right, I'm glad you're keeping it to yourself then. All right, is everybody okay with this? Again, we're not designing all of the columns as columns and frames, just the ones keeping the building up. Okay, so this is a braced frame. Okay, now can anybody tell me what is a problem with using brace frames in building construction? Okay, what did you say? Windows, exactly. And you were talking about stuff getting in the way. You're all saying the same thing. The architect doesn't like having a big brace in the middle. Imagine right here, there was a big diagonal member right there. Now, I'm a steel guy, so I think it would look cool. But that's just me. You know, the architect and the folks responsible with the aesthetics of the building would not like that. Okay? But it doesn't mean you don't use them. I mean, you can use them in very advantageous places. For instance, what if you have an elevator shaft right near there? You don't need windows because it's an elevator, you know? Might be a great place to put a brace frame, right? Or if you have a wall that doesn't have windows, that'd be a great place for it. See, one of the things about brace frames, they tend to be cheaper than moment frames more often than not. Granted, you're using more members, but the connections to affix those members to the frame tend to be a lot cheaper than the connections required for moment frames. You end up needing a lot more welding and a lot more bolting for a moment frame. And the members themselves tend to be a little heavier. Now, let's talk about moment frames. Okay, so obviously the advantage of a moment frame is that there's no braces in the middle, right? So the architect and the owner, they love it. Nice open window spaces. Okay, but there's a couple issues. Okay, first off, I think you can kind of tell. I kind of like this image because you look at this image, you can tell what's the brace or what's the moment frame and what's the regular frame, I guess I would call it. Notice how right here you can see the columns are a little deeper and the beams are a little deeper. Everybody see that? Okay. Over here, they're a little lighter. It's because this system right here is responsible not just for the gravity loads it's seeing, but it's responsible for keeping the whole building upright if wind or earthquakes hit it. Hence why it's a lot bigger. So these would be the columns that I would assess as if it was a column in a frame. These ones over here, I'd probably just go with K equals 1 and move on. Okay? Does that make sense? Everybody okay with that?
How would you, like, where the transition is?
Mm-hmm.
So, which one would you analyze as
Are you talking about the beams or the columns?
the columns? So you have where the transition is.
Like right here. So I'm saying this column would be treated as a column in a frame. This one wouldn't, is what I'm saying. The same thing with the beams, okay? These beams I would treat as simply supported. These beams would be fixed into a frame, and in order to accurately get the moments and shears in these beams, I'd have to break out RESA and do a big RESA analysis, or something like moment distribution or something like that, because that is on this side, you know, these are all simply supported beams. This is a highly indeterminate system, okay? So is that, everybody kind of remember that? Okay. All right. Everybody good so far? That's a good question, and there's no simple answer, okay? First off, it's a function of the building and a function of the demands of the architect and the client. You know, every building's different, so you're going to have to understand how wind and how seismic is going to affect a building. For instance, this building has a very unique plan view. It's a very long building, right? It's not very tall, though. This building is going to behave much differently than something like Smith Hall. Very normally shaped building, pretty rectangular, but it's pretty tall, okay? So this building is going to behave a little differently than something like Smith's. I guarantee you the lateral system for this building is different because the loads and the demands are different, okay? So that's number one. Number two, a lot of where you place moment frames and brace frames, once we've gotten that out of the way, comes from economics and, honestly, experience. For instance, let's take this building. Okay, this building has a moment frame, but based on the image, it looks like that moment frame is really only going across 2 bays of the building. Like there's moment frame here and moment frame here, and that's it. Make sense? If I were to extend that moment frame, you know, over here, and make more of this, you know, moment frame, I would have more moment frame members, but more than likely they would be smaller members. Because think about it like this. more members holding up the building means that each member can be a little smaller, right? But if I've got more moment frame members, that means I've got more connections that I've got to make and more welding that I've got to do. So it's a trade-off, you know, and it just comes with experience and time. There's not really a better answer than that. Did that kind of answer your question now? Well, you're going to, I mean, nowadays you're going to use software to carry out your designs. I mean, if I was a structural engineer in charge of a major building project, let me see what time it is so I'm not staying over. Okay. If I was a structural engineer in charge of a major design project, I'm going to generate a few different alternatives, like a moment frame crossing two bays, maybe one crossing 3, one crossing 4, and then do some rough sizing and some rough calculations, and then for each one of those alternatives, figure out, okay, alternative 2, that's the one that's probably going to be the cheapest, and then move on and finalize my design. Actually size the welds and select the number of bolts and, do all the detailing. You see what I mean? Is everybody else okay with that?
All right, so this is just one side of that building, though, so would it be safe to say that if you're going to put moment frames in that pattern on this side, would you wrap around the corner?
It depends on the demands of the client. Let me say this.
Would each corner have moment frames here, and then the other corner?
All right, let me answer it like this. Okay, so here's a typical building, right? So let's say all we're talking about is wind. Well, this building, looking at the way it's proportioned, it can handle winds coming like this, like that, and like that. It can handle winds coming from all 4 directions because I've got bracing systems along all directions. You need something similar for every other building, right? Because this building would be adequate to withstand loads hitting it from side to side. In other words, it's got a system to resist that. But that it also has to have a system to resist loads like that. If there was no system like that, the building would just topple over that way. Wouldn't matter how strong that is. So you need something. Yeah, you got to have some. Again, architect demands, etc. Your roofing system. Well, not really, because think about it like this. A building is really just one big cantilevered beam sticking out of the ground, right? Fixed on the bottom. Let's say you got a 20-story building, right? And you apply load to it. Well, shear and moment diagrams tell me there's really not a lot going on the roof. See what I mean? I'm not saying it doesn't help. I'm just saying it doesn't really do much. Does that make sense? This is good stuff. Any other questions? Okay. I wanted to give you all a close-up view of the difference between what I'm calling a simple connection and what I'm calling a moment connection. So a simple connection is what you see throughout most of the building, simply connecting beams to columns, etc. So this is a simple shear connection. Now, if you notice, one of the big differences between how this connection is performed and how this connection is performed is this connection is primarily focused on only affixing the web of that beam to the column. Everybody see that? The flanges are largely left unchecked. Sound good? The reason why is because if we're talking about a beam, typically the web is what is transferring the shear and the flanges are what is transferring the moment. Okay? This is a very simple connection and a very cheap connection to produce. Now let's look at a moment connection. This is what would be in a moment frame. Okay, so first off, we have a plate that's attached to the end of this beam. This plate is welded all around. Okay, that takes time. Okay, then we've got what? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 bolts affixing that to the column. That is a fairly expensive connection to make as opposed to a simple shear connection. See, in this moment connection, we're not only connecting the web, we're connecting the flanges as well. It's the flanges that are transmitting that moment. And it's not just the beam that you have to deal with. Look at this. Look at these columns, okay? And look at these columns. See these plates here and here? Everybody see that? Well, if I bend this beam, think about bending moments, I've got a large sort of concentrated force here and a large concentrated force here. Those plates are there to help stiffen that column against those concentrated loads. So you got to put them there too. If you notice, you can kind of see them. You've got something here and something about right there. Make sense? There's a lot more fabrication that goes along with the moment. Granted, you get a lot more open space, but there's a trade-off. It's a little more expensive. So it's all about what makes sense in the long run. Okay? Sound good? All right. All right, so I tell you what. I'm going to show you something real quick, and then we're going to call it. So here is our K values for columns by themselves, right? I want to show you something real quick. So this is I want to look at case A, B, and D, okay? So the reason why I'm looking at A, B, and D is these are the three cases where the ends of the column stay where they are, okay? They don't move. Now look at case A and case B. So both of them are fixed at the bottom. This one's fixed, and this one's pinned, right? Everybody okay with that? So this K value, I'm talking about the theory right now, the K value is 0.5, this K value is 0.7. Sound good? Well, I propose that if you've got a brace frame, let's say this is fixed, right? What about this point right here? Is it fixed? Is it pinned? Or is it somewhere in between? I say it's somewhere in between because I don't think that that upper connection is purely fixed or purely pinned. I say it's somewhere in between. It's a function of the stiffness of the members framing into that joint, okay? If I pinned the bottom, well, this is going to be pinned. Is this fixed or is this pinned? It's somewhere in between. I say the K value is somewhere between 0.7 and 1. Does that make sense? Okay. Now, all I'll say is this, to skip ahead a little bit. How do you determine the K value for a given frame? Well, you use an alignment chart. So the idea is you compute these two stiffness parameters on either end of the column. We call them G values, so a G sub A and a G sub B. The G values are computed based on the stiffness of the members framing into a given joint, and then we strike a line, and I'll talk more about where this model comes from, but we strike a line and we say, okay, wherever that intersects, that's the K value for that given column. That table is, or this chart is in your manual. The problem is it's really tiny, and the manual pages, see how they're curved? So I gave you all a really big one that you can line up pretty nicely. So this is what I mean when I'm saying bring a straight edge. You're going to need it, okay? Sound good? That's all I got for steel. If you're not in concrete, I will see you on Monday. We don't meet on Friday. What's that? Let me stop this real quick.